Can I have a control?
I'm your
Okay.
control.
Okay. Yeah, okay. Well, thanks for coming, guys. So I am Jen. I'm the architect of Nervos, and I'm also a researcher. And at Nervos, we are building a layered network. Okay, by layered network, I mean the network is comprised of like layers of protocols instead of a single blockchain. A single blockchain is a single protocol, and so before I explain our layer 1 blockchain, which is named CKB, I will first talk about like how we define those layers, like what is layer 1 and what is layer 2. Next, yeah. So in our opinion, the key difference between layer 1 and layer 2 is the consensus scope. By consensus scope, I mean how many people, how many nodes participate in the consensus in this protocol. Okay, so like we think layer 1 should have the broadest consensus of them all in this network, and there's only one kind of the most broad consensus, which is global consensus. Like everyone can participate in the consensus in your layer 1 protocol, right? That's what permissionless blockchain are doing. And layer 2 will have a smaller consensus scope. For example, if you consider like Plasma, right? Plasma has only a operator or a BFT like committee. That's several people, several nodes, like 20, 30 nodes. Or if you consider like state channel, payment channel, that's two-party protocol. It's a protocol between two people, right? Or you like for example, or like we can connect like some permission blockchain or consortium blockchain with layer 1 blockchains. And that's also some kind of smaller consensus scope. So why do we do this? Because the consensus is expensive. If we want to have global consensus, the cost for it is very, very high. And if we can sacrifice a little bit of consensus, we can have a huge scalability gain from the consensus sacrifice. That's why we can like have the scalability in a layered network. Next page. Yeah. And there's something I want to emphasize here is that layering is not only a solution for scalability, because layering is a general method for separation of concerns. Like we have different layers and we solve different problems at different layers. That's useful for a lot of problems we face today in the blockchain world. For example, with layer 1 and layer 2, we can have computation on one layer and verification on another layer. We don't need to mix together these two kind of things. Computation and verification is very common things in like cryptography protocol. Like if you think about it, like signature verification, right? Someone is generate the signature, someone verify the signature, or like ZK Snark, right? Someone generate a proof, someone verify the proof. Layering is a very natural match to such patterns, and we can also separate like transacting chains, transacting layer, and value preservation layer, sometimes called like store of value layer. Kevin will talk more about this. And there is a very interesting thing that we can also have compliance on one layer and neutrality on another layer. Like a lot of companies today in this industry want to like be compliant to those financial regulations, right? We want to move assets in the real world, move them onto blockchain. But most of those scenarios can only be implemented on like permissioned blockchain because we need KYC, we need AML. But how can you do that on a permissionless blockchain? How can you do that on a proof of work blockchain? Should layer 1 blockchain also be compliant to those regulations, or layer 1 blockchain should be neutral to those regulations? So we think that maybe the layer 1 blockchain should be neutral, just like internet. Right? Internet is neutral. And actually, you cannot be compliant to all those regulations because, as we just said, like layer 1 blockchain is built upon a global consensus. There are like hundreds of countries on the earth, right? How can you be compliant to all of them? The foundation layer must be neutral, but we can also like be compliant to regulations on layer 2 because it has smaller consensus scope. Okay, next page. Yeah. So with such a definition, can any blockchain be layer 1? Right, that's a question. Of course not, right? Because for layer 1, like what we need is a global consensus, and we can sacrifice some performance or scalability. But we want these two things more than like scalability. We want decentralization. That's important for censorship resistance. And we want security, right? The layer 1 must be the most secure layer in this whole network. It's the security foundation of the whole network, of the whole crypto economy. So typical layer 1 blockchains today are like Bitcoin and Ethereum. That's the two most secure blockchains we have today. And there are actually a lot of public blockchains there, but in our definition, they are not actually layer 1 blockchains because it has smaller scope if you think carefully about them, right? If you compare the consensus scope of those public blockchains with Bitcoin and Ethereum, they have smaller scope. Like some blockchain has 21 nodes, right? 21 validators. Right? So that's why we built CKB, our own layer 1 blockchain, because we think both Bitcoin and Ethereum, they are not perfect for our scenarios. In short, like Bitcoin is nearly perfect, but you really cannot do like programming on Bitcoin. It's really hard to do that. Right? Bitcoin has very limited scripting system and very limited like state model. You can only have Bitcoin on Bitcoin blockchain. We want multiple assets on our blockchain, and the blockchain can like verify proofs submitted by layer 2 protocols. Ethereum can do that, but Ethereum has some other problems, like its token economics we think is not compatible with a layer 1 blockchain. That's what Kevin will explain later. So that's why we built CKB. Okay, it's a permissionless blockchain designed with layer 2 in mind. That's Nervos' approach, because like all the blockchains today are designed for some scenario, like designed for payment, designed for like to be a smart contract platform. But if you agree that the future of crypto economy or the future of blockchain world should be run on a stack of protocols, on layers of protocols, you should design a blockchain in that mindset. You should design a blockchain that with those layers in your mind, right? You should design for layer 2 instead of like I want to design for cash. Because that's different use cases, and if you design for cash or something else, it will very possibly that it won't work very well with layer 2. So CKB is a permissionless blockchain designed with that. And CKB uses a proof of work based Nakamoto Consensus that I will talk today. And CKB has a very abstract programming model with CKB virtual machine and cell model. I will also talk about them. So yeah, next slide. So the first thing I will talk about is like what we call code name, NCMax, which is a maximized version of Nakamoto Consensus. By Nakamoto Consensus, I mean the consensus used by Bitcoin, the simplest one. So we have a guy named Zhang Ren. This guy, he's working on our consensus algorithm. And after we did a lot of research, we found that Nakamoto Consensus is still the best of them all. Like there are so many derivatives, variations of Nakamoto Consensus today, used in all kinds of blockchains. And Zhang Ren developed a new quantitative method to compare them, to compare the properties of all those variations. And the result is Nakamoto's consensus is still the best. If you consider all things, if you include all aspects in your consideration, like including selfish mining in your consideration, you will find that, well, there's no other NC algorithm doing better than the original Nakamoto Consensus in selfish mining resistance. Okay, so we choose to stick on the Nakamoto Consensus, but we can still do something. We can make Nakamoto Consensus better. How? The problem, the bottleneck we find in all those Nakamoto Consensus, or in all, not just in Nakamoto Consensus, in all consensus algorithms, is network bandwidth. Okay, if you think about this is all of your bandwidth, right? And in order to do some like token transfer, you need to send a transaction to the network, and the transaction must be replicated to all nodes in the network, right? That's something you must do. So part of the blue part of your bandwidth will be used to synchronize transactions. That's you cannot avoid. And then after the transactions are synchronized in all those transaction pools, you need consensus to reach agreement on what the next block is. What subset of transactions should be included in the next block. That's what consensus does. And consensus has some cost. You need to like transfer consensus messages between nodes. So that's the cost of consensus. And maybe there's some bandwidth left you don't use. Okay, so no matter what you did, this cannot be avoided. And the most you can do with this part is you eliminate the consensus completely. So it uses 0% of your bandwidth. But that's the extreme, right? Your performance is still bound by the network bandwidth. Say like the average network bandwidth in US today is maybe like 40 megabytes per second. So you cannot send, your TPS cannot exceed that bandwidth. Like each transaction is like maybe 300 bytes, and you can calculate, right, how many transactions you can transmit on the whole network in 1 second. That's the upper bound of your consensus performance. So, okay, now we have identified the bottleneck. Next. And what's the problem? What's the problem? We cannot exceed that. And we can see a very clear problem in our blockchain, which is we call double transmit problem, which is like every transaction needs to be broadcast twice in this network. The first time you broadcast a transaction is the user construct a new transaction and broadcast it to all nodes in the network. The second, pass two, right, is when a miner mine a new block, included your transaction, and broadcast the new block to the whole network. Your transaction will be included, will be broadcast again with that new block, right? So it basically means that we can use like at most roughly like 50% of the bandwidth because we need to broadcast every transaction twice. If we can solve this problem, we can do better. Okay, so how? The idea proposed by Ren is two-phase commit. Okay, so this is a simplified block, and so each block is linked to previous one. And usually, like in Bitcoin, we have a transaction root, which is a Merkle tree root of all the transactions included in the block body. But for two-phase commit, we add a new field in the block header, which is a proposal root. Proposal root is the Merkle tree root of all the proposed transaction IDs in this block. So the process is like I have like A, B, C, D, 4 transactions in my transaction pool. And first I propose like I want to include A and B in some new block in future. So I collect the transaction short ID. It's like transaction ID, the hash of transaction. So I collect the transaction ID of A and B and construct a Merkle tree and include the Merkle root as the proposal root in this block header. And we have another rule, which is we can only commit transactions that has already been proposed by some earlier block. Okay, so you first propose some block, and then you can only commit those proposed transactions. You first propose some transactions. So with this setting, there's a time, there's a time for miners to synchronize those proposals, right? Before, for example, if I see there is a transaction C and transaction D in this proposal tree, in this new block, and I have no transaction C and D in my transaction pool, I can ask the miner to send me transaction C and D when I see this new block. And after 4 or 5 blocks, maybe shorter than that, every node in this network will have proposal transactions synchronized, right? And now any node in this network, any miner in this network can mine a new block and include those proposed transactions in this commit tree. So we commit those transactions, which means the transactions are officially included in a new block. They are valid now. And when I produce, so another miner now, he included the transaction C and D in this commit tree in his new block. And when he mined the new block, he only needs to broadcast the block header. Why? Because all miners in this network has already synchronized the proposed transactions. All nodes already got the proposals. And you only need to broadcast those proposals, the idea of those transactions when you commit those transactions. That's how you can avoid like double transmit problem. Every transaction only need to be transmit once, because you only need to transmit the transaction, you only need to synchronize the transaction before it is included in a new block. And when it's really included in a new block, you only need to synchronize the transaction IDs of those already synchronized transaction bodies, right? That's how you avoid, yeah.
What happens to a proposed transaction that's never committed?
They are discarded, but you can later like propose them again, yeah. Okay. Yeah. You mean mempool? Yeah, there's a transaction pool as like in Bitcoin. There are actually two transaction pools. One is for proposed transaction, one is for not proposed transaction. Yeah. Yeah, there's a mempool. Yeah. Okay. So, yeah. Yeah, please.
Maybe I missed, but could you elaborate a little bit on the synchronization of the proposal route? Because don't the miner, like that synchronization process, don't the miners still need to consume bandwidth to actually synchronize the
Yes.
proposal transaction?
Yes.
Or are you just saying they don't need to broadcast the transaction to the entire network and just the pool of miners?
Yeah, that's a direct connection between miners. Because you received you received a new block from some of your peers, right? So you know who sent you these new proposals, and you just ask them for these new proposed transactions.
Does that presume that if you're a miner, you know who the other miners are in order to establish the connection with them?
Well, your peers may not be miners. So, like, I'm a miner. I mine a new block. I broadcast a new block to some like full node B, and the full node B broadcasts a new block to a miner C, right? The miner C can get those proposed transactions from full node B, and full node B can get those proposed transactions from me. It didn't need to be direct connections between miners. Just use the normal peer-to-peer network. Yeah. Next, yeah. So that's one problem, the double transmit problem. There's another problem, not problem. There's another observation we have. It's like the internet bandwidth is increasing, is always increasing, right? Like Bitcoin was designed like 10 years ago, and the block time, the block size is fixed at like 10 minutes and 1 megabyte block. Maybe we can find some way to make our consensus adaptive automatically to the bandwidth change, right? If our consensus protocol can tweak its own parameters as the bandwidth increase, that would be perfect, right? We can even avoid like all those hard fork stuff, mess, right? Next. So, well, this is in research. We have had some progress. We have had some result. So this is what we call adaptive consensus. So what we want to do, what we want to implement is a consensus that has its difficulty adjustment, targets a fixed orphan rate instead of a fixed block time. Okay. Why? Because the orphan rate is a signal of the network condition of your whole network, right? If you have higher bandwidth or higher latency, lower latency or lower average latency, average bandwidth in your network, your orphan rate will decrease. And in the contrast, your orphan rate may increase, right? So if we target a fixed orphan rate, we can tweak. If we target a fixed orphan rate, we can tweak the consensus to fit the current network condition. So, for example, if the orphan rate is less than the target, it means the network is better than what we think at this time. The network is underutilized. Then we need to decrease the difficulty, which means block interval will decrease, which means in a fixed amount of time, more blocks will be produced, and that will increase the throughput of the blockchain network. Because before the adjustment, there's 3 blocks in 3 minutes, and after adjustment, there is 6 blocks in these 3 minutes. So the block time is dynamic in CKB, in this consensus. Okay? And although the block time is dynamic, we will have a fixed epoch time. By epoch, I mean in Bitcoin it's 2 weeks. The period between 2 difficulty adjustment, we call it an epoch. But we will still have a fixed epoch time. So each epoch will have different number of blocks because we will have dynamic block time. So with these two design, okay, our goal is to have a Nakamoto Consensus that running on an open global network that can reach 100 to 200 transactions per second. It's actually quite hard. Yeah. We are doing some experiments with our prototype, with the adaptive consensus, we hope we can make the consensus adaptive to the network condition and to adjust its own latency throughput according to the network bandwidth increase. Okay, that's about our consensus. The second part is about abstract programming model. So first I want to say, CKB has a very different programming model than Ethereum. Okay. So it's interesting. So why do we need an abstract programming model? Right? Why do we need it to be abstract? Because there is a problem we observed is lack of crypto primitives on layer 1 blockchains. What do I mean by that? First, why is it a problem? Because if you want to build a layer 1 blockchain, right, you need to communicate or interact with different layer 2 protocols. And many of those protocols use novel cryptographic techniques as a component of their protocol, right? Because there are some people propose ZK Snark Plasma in Ethereum community to combine Plasma with ZK Snark, so the layer 1 can verify computation on the Plasma chain, right? But how can you do that without the capability to verify ZK Snark proof on layer 1 blockchain? That's impossible. And different layer 2 protocols will use like different signature algorithms. Some like Schnorr signature BLS, right? And we also need interoperability with other blockchains. Like there are someone proposing like, can we add Blake 2B hash function as a precompile to EVM? Right. The EIP is there for like 2 years, and nothing happened, right? So it's a problem. It's a problem because we always want these new crypto primitives. But in Bitcoin or in Ethereum, the only way you can add a new crypto primitive is to hard fork this blockchain, like add a new opcode to Bitcoin or add a new opcode to EVM or precompile to EVM. That's why we need a abstract programming model. First, the virtual machine in CKB is quite abstract. I will talk about it later. By abstract, I mean we need to push as many things as possible into upper layers and make the virtual machine itself as simple, as abstract as possible. Right? So for why simplicity is important for a blockchain virtual machine is because the blockchain is about security, right? We want blockchain as secure as possible. And simplicity is the best friend to security. If you make things too complex, how can you be sure that it's secure? Right? And simplicity means a lot. Like runtime cost model will be simple. By runtime cost model, I mean like how many gas you should charge for this opcode. That's a cost model. If the virtual machine is complex, it's hard to do that. Take WebAssembly, for example. We don't use WebAssembly. We use RISC-V. We adopt RISC-V instruction set. Take WebAssembly, for example. What if WebAssembly add garbage collection to its specification, right? Do you want garbage collection in blockchain virtual machine? That would be a problem, right? That's also why we think blockchain VM should be low level, right? We don't want garbage collection in our virtual machine. And high level is also a synonym of complexity. And why do we need the virtual machine to be abstract? I just talked about one reason. And or if we state that in another way, is like blockchain is hardware like software. Why? Because it's hard to upgrade, right? Whenever we want to upgrade a blockchain, we need to do hard fork or soft fork. It's hard. It's as hard as you found some bugs in your CPU and you want to revoke those CPU and upgrade those CPUs in your consumer's home, right? It's hard. And if we can make the virtual machine as abstract as possible and push as many things as possible to upper layers, that means we can do a lot more things in user space. And the blockchain can evolve faster because it's always easy to change things in user space. Next. So CKB virtual machine is simple. We just use RISC-V standard. So it's compatible to industry standard. And RISC-V is simple. It has about like 100 core instructions. Compared to like EVM has 139 opcodes, x86 has 1,000 instructions. And it has a simple runtime cost model because we can just measure in like CPU how many CPU cycles is needed for this instruction. It's extremely simple. And CKB virtual machine is abstract. By abstract, I mean there's no hard-coded crypto primitives in CKB VM. No, there's no special opcode in CKB VM. No OP check seek, no easy recover. Well, there's obviously a problem with this design. Is like if you run all the crypto primitives in your virtual machine, it must be slow, right? That's why there's no people do that. But the benefit of adopt RISC-V instruction set is we can do quite good optimizations on this virtual machine because there are a lot of mature research results there. So, for example, SECP 256K1 is our default transaction signature algorithm. It's just a library or a smart contract deployed on CKB. SECP, the signing algorithm itself, is just a smart contract. Like you implement SECP in Solidity and running it on EVM. That's what we did in CKB. And how do we deploy it? We deploy it by compile the standard Bitcoin Core implementation. We compile it into ELF format and deploy it deploy a normal contract in Ethereum. We just deploy it as a contract on CKB. And then all those transactions can reference to this library and use this crypto primitive. And after a fair amount of optimization, we have implemented a baseline JIT, a very simple JIT in our virtual machine. We have decreased the verification time of a single signature verification time to 9 milliseconds. For comparison, the signature verification time on native machine is 1 millisecond. So it's within 10 times, right? That's good enough for blockchain virtual machine because the bottleneck is somewhere else, not here. If you can optimize it into within 10 times. Yeah, next. So that's why CKB virtual machine is powerful. And the power of CKB virtual machine is a fortunate side effect. We actually aim for simplicity and abstract, right? But it's powerful because we adopt RISC-V instruction set. The virtual machine is compatible with the whole GCC toolchain, which means you can use any programming language to program on CKB virtual machine and compile them using GCC to CKB virtual machine instructions. And we support user-defined crypto primitives because even the default transactions signing algorithm is a script, smart contract running on the virtual machine. We believe that other crypto primitives should be okay to run the CKB virtual machine with reasonable performance. And it's even better than that because we are compatible with GCC, right? That means most crypto libraries can be easily ported to CKB virtual machine because most of them are written in C, right, or Rust. They're all compatible with our virtual machine. And it's even better because we don't ask you to implement your own version of the crypto algorithms, right? It's always error prone. It's too easy to have mistakes in your own crypto implementation. Don't do that. Just compile existing mature crypto libraries and use them. And we can also support high-level languages. We provided a demo on GitHub, which is show how you can write smart contracts in Ruby, which is a high-level dynamic language. What we did here is we basically compiled a tiny Ruby interpreter into a smart contract in in CKB. So you can write contracts in Ruby and deploy those Ruby contracts and run them in that Ruby interpreter that is running in CKB virtual machine, which is like pretty cool. Yeah. Yeah. So we have a please.
Was the 9 milliseconds benchmark running on a traditional CPU?
Yeah. Yeah. On like Xuejie's laptop. Yeah. Yeah.
I read somewhere that like one of the benefits of using the RISC-V instruction is that it's very easy to create ASIC miners because like it's really easy to create like an ASIC using the RISC-V instruction. So is that one of your goals? Increase the performance?
That it could happen, but it's not our goal. Yeah, and even it happens, I think it should not have very big effect on the whole mining ecosystem, because the computation intensive part is in the proof of work hash function, not in the transaction verification. Yeah. Yeah.
Just out of curiosity, do you happen to know how that 9 millisecond benchmark compares to if you compile the same library into WebAssembly?
I'm not sure. I think, so we have a benchmark before we did the JIT optimization. It's like about 40, 30 milliseconds on our CKB virtual machine. But although we didn't do JIT, we did some other optimizations. On WebAssembly, I'm not sure, maybe 40, maybe 100, I don't know. Yeah. Yeah, okay, that's the virtual machine, right? And for a abstract programming model, we also need a abstract state model. So the virtual machine is for like computations, for computations. And you need somewhere as a storage for your state, for your data, right? And by the way, so actually, why it's easy to program on Ethereum than Bitcoin? The Turing complete part is it's not the most important feature. The most important thing is like Ethereum has some stateful programming model, right? You can store states in your account. You can write key values in your contract. That's important. In Bitcoin, you cannot reference to some other state in your script, in your pubkey script or any script. You can only do like stateless programming. So if we want to have a really good programming model, we need to have some good abstract state model. And it's very simple in CKB. CKB itself is basically a generalization of Bitcoin, and the state model, the state object, is a generalization of UTXO. By state object, I mean the basic unit of the basic state unit of the blockchain. Like in Ethereum, is account, right? The smallest basic unit of state storage. In Bitcoin, it's UTXO, because we use UTXO to store the value of each coin. And we generalize UTXO because we can only store like integers, value, numbers in UTXO. We generalize it into cell, what we call cell. And you can store any data in cell. So it's not just numbers, it's data. And we also have log. In Bitcoin, each UTXO has a log script. It means who can span this UTXO. Basically, it's a pubkey here, right? We also have a log. And there's a type. That's a bit more complicated. I will skip that part in this talk. But if you're interested, we can talk later. Yeah. And the transaction structure is similar to Bitcoin. Inputs, outputs. you have inputs in your transaction refer to outputs, previous outputs in other transactions, and you have cell as your outputs. So each transaction each transaction means a state transition in this whole network, right? We remove some old state. This old state are removed from the blockchain, and we add some new state, because each cell is a state object, contains new state. Next. Yeah. So if we look inside a transaction, each input reference to there is a cell reference in input, which is basically the transaction hash and the output index of your previous cell, the cell you want to update. And in each input, you have an unlock proof to prove that I have the privilege to update, or to update that previous output, to update that state, to update that cell, right? It's quite similar to Bitcoin. Like Bitcoin also has a reference, and in Bitcoin, this is here is signature. Your signature proof you have privilege to spend the previous output. But now in CKB, it's the signature that prove you have the privilege to update previous state. And you put your new state here, right? This is the new cell, contains the new data. You just put anything you want here, your new data here in this output, and attach a new log script to specify who can update this cell in future. Like in Bitcoin, who can spend this coin in future, right? So the whole thing is quite similar to Bitcoin. One consensus rule here is all those bytes in this cell must not exceed the capacity specified in this cell. So each cell has 4 fields, and one of them is capacity, specify this cell is 100 bytes at most, right? So all those fields together cannot use more than 100 bytes. And this means the cell capacity is the native asset in this system. Like, if I told you I have some tokens in CKB, right? What do I mean? It means I have 100 CK bytes in this system. We call it CK bytes. You may have 1 kilobytes in this system, and you can use it as you wish. You can use all of them to store your state, or you can I have 100 CK bytes. I only use 50 bytes of them to store some data, store maybe my pub key. So Bob can verify my signature after synchronize the CKB blockchain using a light client, right? Because he can get my pub key by synchronize CKB blockchain, and he can see my pub key in this cell. Okay, that's some example. Next. Yeah, so that also means the state size of the blockchain will always less or equal than the total capacity in circulation. Remember, the capacity is the native asset in the system. So the total state size is bound with the token in circulation. That's the start point. That's the start point. The cell model and this bound is the start point of our token economics. We have this bound because we want to solve the state explosion, state bloating problem in blockchains. If you synchronize Ethereum or Bitcoin is better. If you want to synchronize Ethereum blockchain, you will find maybe you need hundreds of gigabytes or even terabytes of disk to synchronize, right? Because in blockchain, there's a problem that everyone can write data into blockchain, and every node in the network has to keep that data for you for free forever, right? That's a problem. How can you solve that problem? This is the start point. I'll skip this part. It's a little bit yeah, this is well, in short, in CKB, the nodes verify a new transaction by running all those scripts inside each cell. Like, it's like Bitcoin, right? How Bitcoin node verify a transaction is by running like the script in input and output. And if all the script returns like 0, the transaction is valid. If any of them returns like 1 or non-zero, the transaction is invalid. It's the same in CKB. We just generalize Bitcoin a little bit. Yeah. Okay, so now you should have a general idea about CKB. And one thing I want to point it out, one thing important I want to point it out is why we have such a architecture is because we think it's the best fit for our layered architecture. It's the best fit for the layer 1 and layer 2 design. Why? Because so blockchains today, there are basically 2 kinds of design. One of them, I call it state transaction. Okay, consider this is Bitcoin, state transaction. Bitcoin has state transaction. Why do I call it state transaction? It's because in Bitcoin transaction, the new state is included directly in the transaction. The new state is the new output generated by your wallet, right? When you construct a new Bitcoin transaction, you find some previous outputs, you attach signatures to those outputs, and you have some new outputs. Those new outputs are new states in Bitcoin. Right? Next. And on the other hand, there's what we call event transaction. This is what Ethereum did. Okay. In such a system, in its transaction, there's only event included in this transaction. Okay, so what do I mean by state and event? So state and event is the state and event in state machine, because blockchain networks are distributed system, right? And we can use replicated state machine model to model any distributed system. So in a replicated state machine, we use consensus to order all those transactions. And each node just execute that order, apply the transaction in order. And each node will reach the same result eventually, reach the same state eventually, right? Like for example, like there are 4 people here, and each has a calculator in his or her hand. So what consensus does is order commands to that 4 people, like +1, -2, multiply 10, right? And if each people execute the command in this order, they will see the same number, same result on their calculator, right? Or we can do this in another way. The commander can like broadcast message like type 10 on your calculator. or type 100, and then type 200, and then type 3. If each people do the same, they will see the same result eventually as well. But these two designs different because in the first design, what my command is like +1, which is an event, is an action. I ask you to execute. In the second example, what I ask you to do is just type 100, type 20. It's the result, right? I just told you result. You just type them on your calculator. So by event transaction and state transaction, yeah, that's example for what I mean by this. So Bitcoin use state transaction, and Ethereum use event transaction, because in Ethereum transaction, there's only data, a field called data in Ethereum transaction, which means basically a message to smart contract, which means like I want to compute 1 + 1. And it's the miner need to do the computation and generate the new state, which is 2, and store it in the account, right? There's no new state included in the event transaction. There's only event in the event transaction. Okay, next. So why is this important? It's because with state transaction, we will reach off-chain computation, on-chain verification naturally. So for example, the upper half of the picture is like Ethereum use event transaction. There's only event included in transaction. And when user want to transfer some tokens, what he did is he triggered some like transfer event to like his wallet, right? And then his wallet just include this information in the event transaction, which is like from Alice to Bob, value is 10 coins, 10 tokens. And it's the miner do the computation and generate the new state. Right? The result is generated remote on miner's machine. And okay, so for comparison, in Bitcoin, in CKB, or in any system use state transaction, when the user wants to transfer some tokens, he also triggers an event, like I want to transfer 10 tokens to some other people, and the wallet receives the event, and the wallet will do the computation. Like think about Bitcoin. The user told the wallet to transfer 10 BTC to other people, right? The wallet will search for my existing UTXOs and generate new UTXOs and construct those old state and new state into a single transaction and broadcast the transaction to the network. And when the user broadcasts the transaction, he already knew the result is those new UTXOs. It's the same in CKB. The computation happens here. The state are generated off-chain. And what the CKB network did is only verification. So we can also take Bitcoin for example. What is verification? It means I only need to verify the sum of inputs equals to the sum of outputs. The verification is different from computation. For computation, we need a like search algorithm and do some computation to generate the new state, new output. But for verification, we only need to compare the equality of sum of inputs and outputs. You can easily see the asymmetry here, right? So this is important because if we can separate generation and verification, it's also a separation of layers. Like if you think about it, like plasma chain, state channel, what they are doing is like generate new states. generate a lot of new states. And what layer 1 is doing is like, okay, you generate 1,000 new states, and I don't care 99% of those states. I only care the final one, right? Only submit the final state back to layer 1, and I can verify that state is correct. That's what layer 1 did. Right? Layer 2 is good at generation. Layer 2 has smaller consensus scope, has higher throughput, has lower latency. They are good at generation of new state. They are good at computation. And layer 1 is slow, is secure. They can do verification occasionally. That's right. That's why we choose like state transaction in CKB, because that's the natural result of this choice. And it's good for a layered architecture. Next. So, so CKB is basically a general verification system, not a general computation system. Ethereum is a general computation system. CKB is a general verification system. Bitcoin is a verification system. Okay. Yeah, we can skip this because Kevin will talk about this. First class asset, first class state. Next. Yeah, that's all for my talk. And we have open sourced all the code on GitHub. If you are interested, you can already clone the repo and compile and run them up, run the node up. Yeah, and we also have a RFC process, request for comments. So we write a lot of technical documents and put them on GitHub. And if you are interested, you can check them. And yeah, thank you.